Hello, everybody, and welcome to Unit 7 of Regents Chemistry, where we'll be talking about chemical bonding. So, today we'll start with the first type of bonding, which is ionic bonding. So, a chemical bond is basically just an attractive force between atoms or different ions, and those attractive forces are established when electrons are either shared or transferred between different atoms or ions. Now, the key thing to remember here is that whenever we talk about bonding, the only type of electrons that we are concerned about are the valence electrons, which, as we all know, are the electrons in the outermost shell of any atom or ion. And why do electrons want to form bonds? Because of this very important thing that we talked about when we were talking about atoms, the octet rule, which means all of the atoms in the periodic table want to have 8 electrons in their outermost shell, or 8 valence electrons, and that's why they either uh, gain electrons or they get electrons transferred from any other atom, or they just share it with any other atom or ion to just so they can have 8 valence electrons. So another very important thing to remember here is that when we have a chemical bond forming, so we have two atoms coming together to make a chemical bond, that is when energy is released. So that's an exothermic process. However, when we already have a chemical bond established, and let's say that the bond is now breaking, those two atoms are now setting free, then that type of reaction is an endothermic reaction because the energy is now being absorbed. That bond needs a lot of energy in order to break. Now, finally, another super important thing to recall before we actually start talking about the bonding, the ionic bonding, are the Lewis structures or the electron dot diagrams, which are basically just the way of showing how many valence electrons do we have in something, and we just use the dots to show those number of valence electrons. And how do we write them? We just start off with the symbol of the element. So in this case, let's say it's element X, whatever that element is, and then we just start drawing the dots around that element to represent the valence electrons. The maximum that any element in the periodic table can have are 8 valence electrons. So let's say that this one also has 8 valence electrons. We'll just go ahead and make those 8 dots to represent the number of valence electrons. So let's say we are now looking to draw the valence diagram for nitrogen. So nitrogen has 5 valence electrons. We'll start off by writing the symbol, and then we'll just make all the dots to represent those 5 electrons. So 1, 2, 3, 4, and 5. There you go. That is the electron dot diagram for nitrogen. Now there are 3 different types of bonds. We have the ionic bonding, covalent bonding, and metallic bonding between the atoms. Today we'll start off by looking at the ionic bonding. Now, as you guys might have already guessed by looking at the name Ionic, this has something to do with the ions. And if you guys look at this picture here, what we see here is that we have a sodium atom, and the sodium atom is losing one of its electrons. And then we have a chlorine atom, and the chlorine atom is gaining that electron. So remember what happens when an atom loses or gains an electron? It becomes an ion, right? So let's start off by looking at the cation. Remember, we said that cations are the positive ions, and they are formed when we have an atom that loses electrons. And metals, for the most part, tend to lose electrons. Metals are on the left-hand side of the periodic table. So let's say we are looking at calcium. Calcium has 2 valence electrons, and those 2 valence electrons are going to be lost. Calcium is going to lose those 2 electrons because that's what's easier for calcium in order to gain a stable or noble gas configuration. So this is what the calcium ion is going to look like, or the calcium cation is going to look like. And because now calcium lost that valence orbit, when we draw the Lewis diagram or the electron dot diagram for calcium, we just don't show any dots for that. Okay, so because those two electrons that we had in the electron dot diagram are now gone. So when we write the electron dot diagram for calcium ion, there will be no dots at all. Now, on the flip side, when we talk about anions, remember that nonmetals for the most part tend to form anions because it's easier for them to gain electrons rather than losing them. And they're on the right side of the periodic table, so they normally make negative ions. And let's look at phosphorus. So phosphorus already has 1, 2, 3, 4, 5 valence electrons. Now, it's easier for phosphorus to gain 3 more and then become a negative ion. So phosphorus is going to go ahead and gain 1, 2, and 3 electrons. So it's now becoming an anion with a -3 charge because it's gaining 3 electrons. When we write the electron dot diagram for phosphorus now, remember we already have those 5 valence electrons and then we are adding 3 more in there. So the electron dot diagram for the phosphorus anion is going to have 8 dots because it has a complete octet. So ionic bonds are basically the forces of attraction between oppositely charged particles or oppositely charged ions. Um, and electrons, these bonds are formed when electrons are transferred from one type of ion to the other type of ion. So one of them is losing electron and the other one is gaining that electron. So the electron is being transferred. And the reason why that's happening is because both of them want to have a noble gas configuration. Now, a very, 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 very important thing to remember is, as we just said, that anions, for the most part, non-metals are the ones that form anions, and then metals, for the most part, form cations. So, we it is safe to say that whenever we are looking at a binary compound, which means a compound that only has 2 atoms, then ionic bond is a bond between a metal and a non-metal. So that's a very important thing to remember. And you guys will know that eventually in like a little bit when we talk about the other 2 types of bonding, that why is it like a very quick hint. If you're given a compound and you're asked to identify whether you see ionic bonding or covalent bonding or metallic bonding, what type of bonding do you see in there? The first thing that you can look for is whether it's a bond between a metal and a non-metal, because if that is the case, then it's an ionic bond. And so finally, the compound that we get as a result of an ionic bonding is an ionic compound. So here we have a quick example. We are looking at a sodium ion that only has a sodium atom that only has 1 valence electron, and we have a chlorine atom that has 7 valence electrons. So as we all know, what's going to happen here is that sodium is going to lose that 1 electron and chlorine is going to gain that 1 electron. So the electron will be transferred from sodium to chlorine. Now, when that happens, sodium forms a positive ion and chlorine forms a negative ion. So this is what that is going to look like. And remember that because sodium lost all of its, like sodium doesn't have that outermost shell anymore, that's why we show no dots for sodium, which is the cation, and chlorine is going to have 8 dots because it now has a complete octet. Now, those ionic compounds that result from ionic bonding are electrically neutral. What that means is that the overall charge on those compounds is 0. So they'll have the same positive charge as much as they have the negative charge. So the overall charge has to be 0. And remember, we said that they are between a metal and a non-metal. Salts, for the most part, are the compounds that have ionic bonding. And the difference in electronegativity between the atoms that we have in an ionic bond is between 1.7 or greater than that. So that's a huge difference. Remember, recall from this from the previous chapter when we talked about electronegativity, that it's the ability of an atom to attract electrons. So that means if we have, let's say you're talking about sodium and chlorine, because it is attracting more electrons, is going to be and it is actually a lot more electronegative compared to sodium. So when we go to table S and we look at the numbers or the values for the electronegativity of chlorine and sodium, it's going to be either 1.7 or higher than that. And that should give you another hint that this is an ionic compound. If, let's say, you have to figure out that what type of compound is this. Okay. Um, so as we said, a more electronegative atom will take the electron. Why? Because that's what the definition is, that because it's more electronegative, it has more ability to attract the electrons. Now, when we looked at that example of sodium and chlorine, that was pretty simple because sodium only had one electron, it was transferred to chlorine, and chlorine now had complete octet. But sometimes it's not that straightforward and it's not that easy. Because here's what happens. Let's say we are looking at an example between calcium and phosphorus. Okay, here we have calcium that has 2 valence electrons, and here we have phosphorus that has 1, 2, 3, 4, 5 valence electrons. Now, we want to know, both of them definitely do want to have a stable or complete octet. Calcium does want to get rid of those 2 electrons, and phosphorus wants to have 8 valence electrons. Okay, so phosphorus, because it's a nonmetal, it is going to gain electrons, and calcium is going to lose those 2 electrons. So let's start by looking at how the bonding between these two are going to work. So step number 1 would be calcium is going to donate those 2 electrons to phosphorus. So this calcium is losing those 2, and they are going to phosphorus. This is what that's going to look like. Now, calcium has a positive 2 charge because it just lost 2 electrons, and phosphorus now has those 2 electrons, but it still only has 7 valence electrons. It needs 1 more. So what can we do in that case? Well, we can go ahead and take another calcium. Now, that calcium is going to donate 1 of its electrons to phosphorus. So now phosphorus has a complete octet, and it has a -3 charge because it has 3 electrons. It has 3 extra electrons, and it has 8 valence electrons. It has a complete octet. However, we now have a calcium that only has 1 valence electron, so it's very unstable. It wants to donate that. So what we can do now is we can bring another phosphorus. Now that calcium is going to donate its electron to phosphorus, and this is what that's going to look like now. Now we have another calcium, which is also an ion, and we have a phosphorus that now has 6 valence electrons. Still needs 2 more to become stable. So what can we do now? Well, we can go ahead and bring in another calcium. Now this calcium is going to go ahead and donate both of its electrons to phosphorus as well. And now that phosphorus is going to be complete. The calcium is also going to become an ion. And here we now finally have everything complete. Like the calciums are stable and the phosphorus is also stable. So overall, we have used 3 calciums and we have used 2 phosphorus. So when we write this, what you guys see on at the bottom of this slide here is Ca3, which means we used 3 calciums, and P2, which means we used 2 phosphorus. Okay, that's all that this formula is telling us. And that, ladies and gentlemen, is called the chemical formula of a compound. So chemical formula is also known as the formula unit because it's like the lowest ratio between the different the different atoms that we have in that compound. It does not represent only one molecule or only one compound. For example, if when we talk about NaCl in this formula, we are only saying that we have 1 sodium and 1 chlorine. However, that does not mean that this is what the whole compound is going to look like, because in reality, sodium chloride is salt. So in reality, this picture that you guys see on the slide is what sodium chloride normally looks like. All it says is that we have 1 sodium bonded to 1 chlorine. That's what this formula is telling us. But that chlorine is going to be bonded to another sodium, and then that sodium is going to be bonded to another chlorine. Chlorine is going to be bonded to another sodium. So that way it just forms like a whole structure. So when we write the formula, all that we are saying is that this is what one bond or one specific part or geometry of that compound is going to look like. Now, while we are talking about the chemical formula, some of the important terms to remember are a coefficient. A coefficient is a number that's given with a compound in like a chemical equation or something, and that just tells you how many of that specific substance do we have. So for example, here it's just telling us we have 2 moles or 2 molecules of sodium chloride. And then we have a subscript, which is that small number at the bottom with the element with the symbol of each element, and that just tells us how many atoms of that element do we have in a compound. So in this case, we are looking at H2O, which is water. So this formula is telling us that hydrogen has a subscript of 2, so that means we have 2 atoms of hydrogen, and oxygen doesn't have any subscript, so that means we have 1 atom of oxygen in a compound of water. And then finally, we have the oxidation numbers, which are given if you guys go to your periodic table and you look at the upper right hand corner for each element, you guys will find some numbers, and those numbers are the oxidation numbers, and they tell us that what are some of the charges that those elements can take when they become ions. So if you go ahead and find calcium in your periodic table, you'll notice that calcium only has an oxidation number of +2, which means calcium can only form an ion with a charge of +2. However, if let's say we look at iron, which is Fe, you will see 2 oxidation states for iron, which means iron can lose 2 electrons and make an ion with a +2 charge, and iron can also lose 3 electrons and make an ion with a +3 charge. So iron has the ability to make 2 different types of ions. So that's what the oxidation numbers tell us. Now, sometimes we also see some compounds. So these are pretty simple compounds. Like you see sodium chloride, we only have like a sodium and a chlorine. Both of them are elements, and they make ions, and we just clearly see the bonding. But sometimes what happens is that we have an element or an ion which is forming a bond with a polyatomic ion. Now, polyatomic ions are the ions that have more than 1 atoms, and you guys don't need to memorize any of them because they are given to you in table E. This is what table E looks like. We have a whole bunch of polyatomic ions in there. So this is how those work. So let's say we are trying to write a formula for an ionic compound which has sodium and it has a hydroxide ion. So sodium, as we all know, is in group 1. It's a metal, so it's going to uh, become a cation with a charge of +1 because the oxidation number is +1. So here we know sodium is going to be a positive ion. And then we can go ahead and find hydroxide from table E, and we can say when sodium and hydroxide ion makes a bond, which means sodium atom loses an electron and hydroxide ion gains that electron. Overall, this is what the compound is going to look like. There you go. So pretty simple, pretty easy, but just sometimes you might get confused by thinking that, well, oxygen and hydrogen are 2 different elements, so why are they together? That's because it's a polyatomic ion. And if you ever see a situation like that, this is the table that you should be coming to. So while we were talking about writing the chemical formulas, there are some things to keep in mind for writing the formula for ionic compounds more specifically. So remember that all compounds are neutral, which means we should have the same number of positive and negative charge. If that is not the case, then we use the crisscross method. So here's what I mean by that. Let's say we are talking about a bond between sodium and chlorine. Sodium has a charge of +1, chlorine has a charge of -1. Both of them cancel each other out. Overall, the charge is 0. So when we write this formula, we'll just say we have one sodium and we have one chlorine in each compound. Okay. However, when we are talking about magnesium and chlorine, now magnesium has a charge of +2 and chlorine has a charge of -1. So when we write the formula for that, we bring their charges down to the opposite side. So chlorine is going to get a subscript of 2. Why? Because magnesium has a charge of +2. And magnesium is going to get a charge of 1 because magnesium is going to get a subscript of 1 because chlorine has a charge of -1. So overall, this is what the formula looks like, MgCl2. And that's because we did the crisscross. So all you have to do is bring down the charges. So the charge of magnesium goes down to chlorine and become its subscript, and the charge of chlorine comes down to magnesium and become its subscript. And another super important thing to remember is that positive ions are always written before the negative ions. So we can't write Cl2 first and then go with Mg. We have to write magnesium because it's a positive ion, and then write chlorine because it's a negative ion. Finally, let's talk about some of the properties of ionic compounds. So first of all, very important thing to know is that they form crystalline solids, which means they are arranged in regular patterns and make like these three-dimensional structures. For example, these that you see right here. They are very, 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 very strongly bonded. So ions are like together in very strong bonds. And very important thing to remember is that they have high melting points. Ionic compounds have high melting points. That's a very important thing to remember. And then finally, do they conduct electricity? And that's a very important concept when it comes to bonding. Remember, whenever we talk about conductivity or conducting electricity, that means we are allowing the charges or electrons to move. So when ionic compounds are in their solid state, the ions are locked together because they are so strongly bonded. So they cannot conduct electricity in the solid state. They're insulators. However, when they are molten, when they're melted, that's when the ions are allowed to move a little freely and they can conduct electricity only when they are melted. Or if they are dissolved in water and they make aqueous solutions. So remember, aqueous solutions are the solutions of anything with water. So when those ionic compounds, let's say when salt is dissolved in water, it is going to conduct electricity. Because now, once again, ions are free to move, so it's easier for them to conduct electricity. Alrighty. So that was it for this part of the chapter. Good luck. I'll see you next time.